All right, so last time we were talking about the magnetic field inside of a solenoid. So what we're going to talk about today, or at least at the beginning, is we're going to start by finishing that discussion. Do keep in mind that the material covered today is the last of the material that will be on the midterm next week. I think it's next week. God, it's already that close. Right, so we're going to finish chapter 4 today and push on to chapter 5. Chapter 5 won't be covered on the midterm, so just want to let you guys know that. So we established last time that the magnetic field, inside a long solenoid is parallel to the axis. So what we have is we have our currents. This is a standard picture of a cross section of a solenoid. So the magnetic field runs something like this direction. Now, what we didn't establish is we didn't establish the strength of the magnetic field inside the solenoid. We already know how to calculate the strength of the magnetic field at the center of a solenoid. We've done that calculation. But what we haven't done is the strength of the magnetic field near the edges. So, as I mentioned last time, it's very possible that the magnetic field would be stronger near the edges, say because it's closer to the wires or something like that. So we need to establish how the magnetic field changes as you go to different radii inside the solenoid. So to determine that relationship, what we're going to do is we're going to use Ampere's law inside the solenoid. So what I'm going to do is I'm going to draw one part of our Amperian loop along the center line, another part up, radially outward, another part horizontally over, and then we're going to finish up the loop this way. So the point is that this Amperian loop will probe two things. It will probe the magnetic field some distance, say r, away from the center, and it will probe the magnetic field at the center, because the magnetic field will contribute to the top part of the loop integral and to the bottom part of the loop integral, and it won't contribute to the left and right side. So what we can establish from Ampere's law here, Ampere's law is that B dot dl is equal to mu naught I enclosed. Using this loop, I enclosed is 0 because the only currents are these circles with dots and X's in it. And so we have that the magnetic field integrated along the loop vanishes. And so we can use that to figure out how the magnetic field on the top relates to the magnetic field on the bottom. So this is equal to an integral over the top. And here this would be, we'd have a minus sign because the magnetic field, we're going to assume we're going this way around our loop, by the way, just so we can pick a direction. So you'd have a minus sign up top because the magnetic field points in the opposite direction. So here we have B top minus B top times, say, the length L, plus B bottom times the length L, plus 0 plus 0. So here we have this is the integral along the top part, B dot dl. This is the integral along the bottom part, B dot dl. This is the integral along the sides. And the integral along the sides vanishes because the magnetic field is perpendicular to the path length vector. So what we find is that B top has to equal B bottom. And we already know what the magnetic field is along the bottom of the loop. In particular, that's the magnetic field along the center line of the solenoid. So this indicates to us that it actually didn't matter where we put the top part of our loop, i.e. the amount that the magnetic field, or the magnitude of the magnetic field any distance away from the center line of the solenoid is constant. And we've already established that the magnetic field doesn't change as you move left and right, right? It's always the same magnitude regardless how far to the left or how far to the right you are, because it's the long solenoid. And we just established that the magnetic field doesn't change whether you go up and down the solenoid. So what that means is the magnetic field just doesn't change anywhere inside a long solenoid. So if we know the value of one place, which we do, this is like we've already calculated the centerline value, then that tells us that the magnetic field everywhere inside the solenoid has that value. And we're going to compute that again using Ampere's law, by the way, in a little bit. Right. So the next thing that we can do is we can use the same sort of procedure outside of the outside of the solenoid. So we also can establish that the magnetic field is, just by doing the same sort of picture, just a different loop out here, we can also establish that the magnetic field has to be constant outside the solenoid for the same reason. There's no enclosed charge, and so the magnetic field here has to be the same as the magnetic field there, because then they cancel out. And so because the magnetic field is constant outside the solenoid, and we would like that the magnetic field is 0 infinitely far away, that means that the magnetic field is 0 everywhere outside the solenoid. Now, again, this is only true for an infinitely long solenoid, but this is a very, very simple approximation that we can make, and it's a good approximation. Like if you have a long solenoid, the magnetic field outside that solenoid is going to be very small. So a solenoid then kind of breaks up the universe into two places, into two regions. There's the region inside the solenoid, which has some magnetic field, which we can compute. And there's the region outside the solenoid, which has magnetic field 0. Obviously, that's only true if that solenoid is the only thing in the universe. Once you have more than one solenoid, then you have superposition of fields and so on. But for the most part, solenoids have very, very straightforward magnetic fields. So now let's actually just compute the magnetic field inside the solenoid. And so we're going to use Ampere's law again. This time, we actually are going to enclose some charge. I'm actually going to do a redrawing here because it'll be a little bit more straightforward that way. Sorry, not some charge. We'll enclose some current. So we know that the magnetic field is constant on the interior. Hence, it has all of the lines are equidistant. And I'm just going to draw some loop that encloses some of the current. So you have current going into the screen here, right? And so some of that current is passing through a loop, and you can't move that current outside of the loop because it's a closed circuit, right? This current goes around here and goes like that, right? So it can't really escape. So this is truly enclosed by the loop that we've chosen. Right. So let's say that this has length L. And let's just compute now. Let's use Ampere's law. So using Ampere's law and the symmetries that we've already established, so we've established that the magnetic field has to point perpendicular to the plane of the solenoid, and it is constant, and it's always, yeah, those two things that we've already established. we can use those to simplify the formula that we get from Ampere's law. So Ampere's law is the statement that the integral over a loop of b dot dl is mu naught times I enclosed. Now we can simplify this. The left-hand side becomes an integral over the loop. Well, this is what the left-hand side is. This becomes an integral over the top of b dot dl plus an integral of the right. I'll just do an integral of the sides of b dot dl plus an integral of the bottom of b dot dl. Okay, so the top, we know that the magnetic field is not zero inside the top, or at least it doesn't have to be zero. And we know that the magnetic field, oh, let's choose a direction, by the way. Let's just choose that direction. We didn't have to choose that direction. It's just a choice I'm making. So we know that the magnetic field with this choice of direction points in the same direction as dl. So b dot dl just becomes the product of their magnitudes. And the magnetic field is constant, so we can factor the magnetic field out of the integral. And so what we're left with is the magnitude of b times L, which is the length of that segment. And then for the sides, we get that we get 0 here. This is because the magnetic field is perpendicular to dl. The magnetic field runs to the right. On the sides, it either runs up or down, so they're perpendicular, so the dot product is 0. And then on the bottom, we have that the integral, we have the integral part, we have the bottom part of the integral also vanishes. In this case, it's because the magnetic field is 0 outside of the solenoid. It's 0 everywhere. So the integral of 0 dot dl is just 0. And so what we find is the left-hand side is just equal to the magnitude of b inside the solenoid times L. Now, what about the right-hand side? So we need to figure out how much current is enclosed. So we're going to assume that each of these turns has a current I running through it. So you would say, oh, well, that has 3 times I current enclosed. But in this case, this is just a schematic picture. So in fact, we need to figure out how many turns there are enclosed in a length, enclosed in a loop of length L. So from the right-hand rule, we know that the current going into the page are considered positive, right? So we use the right-hand rule. So current that's going into the screen is positive. So these are all positive. I'm going to mark them as pluses here. They all positively contribute to the enclosed current. And then we can figure out how many of those enclosed currents there are. So let's do that. So first, I enclosed here is positive. Now, second, let's assume that that the loop encloses n wires, capital N. Might be 3, like it is in this drawing. It might be 38, whatever. And obviously, the longer your loop is, the more wires you're enclosing, right? And each of those wires have current I. Then I enclosed is just n times I. So Ampere's law gives the following. Gives b, the magnitude of b, times L equals mu naught times ni. And so we can solve for the magnitude of the magnetic field inside the solenoid as mu naught n over L times I. And now think back to when we were first talking about solenoids. The useful thing that we talked about was the number of turns per meter, i.e. how many turns are there in a particular length. And we gave this, that's n over L, we gave that the name little n. So the magnitude of the magnetic field is actually just mu naught times little ni. And this is indeed the result that we derived for the center of the solenoid. But this tells us that this is the magnetic field everywhere inside the solenoid. So indeed, we actually needed Ampere's law in order to get that, because we needed Ampere's law to tell us that the magnetic field inside at any point inside the solenoid is constant. Right. So there's an example that you guys should probably check out. It's in section 4.5 in the textbook. It's about a toroidal solenoid. So a toroidal solenoid is a solenoid that you've curved back in on itself. So it forms a donut. And it asks you to find the magnetic field inside that, which is interesting. Yeah, little n is the density. This is turn density. Right. So there's one more thing to talk about with regards to Ampere's law before we proceed into chapter 5, and that's the local form of Ampere's law. So up until now, we've talked about integral forms of all of these things, Gauss's law and Ampere's law. What we haven't done is we haven't given a local form for Ampere's law yet. So the local form for Ampere's law can be derived in much the same way that we derived the local form for Gauss's law. And that was, so for Gauss's law, what we used was we used the divergence theorem to relate the surface integral over a closed surface to the volume integral of the divergence inside that surface. There's a related theorem from calculus known as Stokes' theorem that we're going to use to relate the integral along the boundary, along a loop, to the curl of the stuff inside the loop. So just as a quick reminder for Stokes' theorem, so for a vector field F, this is any vector. What I'm about to do applies for any vector field, which will include the magnetic field. And a surface, call it S, with boundary. You may have not seen this notation before, but this is what it's typically referred to as. So it's like a partial S. It means that it's the edge. So the picture here is, and I'll draw a picture. We have the following. I'll draw a picture before I write the equation. So the picture here is you have some surface. This line is partial S. Inside is S. And then you have some vector field that's, you know, inside your surface everywhere. And in particular, it's also along the edges. So partial S is just like the edge, the edge of the surface. So Stokes' theorem then is the following statement. You have an integral over S. So that would be like dx dy in this case. And it's the curl of F dot, and here's the math notation. We're going to use the notation that you may have seen in math, dot n dA, where dA is like dx dy or r dr d theta or whatever. This is equal to an integral over the closed boundary of S of f dot dl, where dl runs along the boundary. So in our language, we just say, sorry, that A shouldn't have a vector over it. We say that n hat dA, we just call that dA vector. And so what we'd be left with is, and we simplify some of these symbols. So we're left with the curl of F dot dA is equal to an integral partial S F dot dl. So this is the Stokes' theorem. Yeah, so we're going to plug in Ampere's law, right? Because Ampere's law is this stuff over here. So applying this to Ampere's law, we have that an integral over the loop, the Amperian loop of B dot dl is equal to, and I have to put a bunch of words. That's our language. It's just the language that physicists use. It's like less formally mathematical. So this integral is over the surface enclosed by the loop. So basically, we started off with just a loop, and then this integral is over the stuff inside the loop. And this is an integral of the curl of the magnetic field dot dA. So now we have to ask the question, yeah, it can be any surface enclosed by that loop. So in particular, if you have some like loop in three-dimensional space, it could be this surface, the surface that goes up, or it could be just the surface, or it could be the same surface that goes down. It doesn't actually matter which one, as long as it's the same surface. Because, and that should make sense, right? Because the magnetic field that, I'll just leave it at that. But as long as it's the same, as long as its border is the same, it doesn't actually matter. And that's actually a deep result from vector calculus, but we'll put that aside. So what about the current? What about the right-hand side of the Ampere's law? So just as a quick reminder, that's an I. Recall that the current is defined to be the current for like the current passing through some real world conductor is defined to be an integral of the surface, integral over a surface, over a cross section of the current density dotted into the area vector. And so we can input this to the right-hand side of Ampere's law. And what we end up with is an integral over the surface. This is the surface enclosed by the loop of the curl of B dot dA is equal to an integral over the same surface, because this is the current passing through that surface, right? And it's so in this case, it's the same right-hand side. Yes, sorry, right-hand side. This is the same surface. So in this case, it's mu naught J dot dA. And so because this holds for any possible surface, right, it doesn't actually matter, like the loop that we chose here doesn't matter because this applies for any loop, and hence it applies for any surface, we get the local form. We get that the local form of Ampere's law is the curl of the magnetic field is equal to mu naught times the current density. This is Ampere's law, the local form. Great. And it's useful, right? Because if you know the magnetic field everywhere, that can tell you how much current there is at any given place. Because we know that that current, well, okay, this is only true if there's if the magnetic field isn't changing with time. We'll see how if the magnetic field changes in time, we'll see how that affects this formula later. Right, so with Ampere's law all said and done, we're gonna move on to time-changing magnetic fields. It's J's current density. Yeah, this is basically magnetostatics. Now we're going to start talking about electro and magnetodynamics. So the first thing we're going to talk about is magnetic conduction, and that's going to be the subject of today's lecture. And magnetic induction is really a broad topic. It covers a lot of things, and we may not even get the chance to finish it today. So, but we're going to do our best, right? So before up until now, all of any circuits that we've talked about have always had a battery as the source of EMF, right? And, you know, I mentioned that there are other sources of EMFs, like you could have like a water wheel turning and so on and so forth, but we didn't actually go into the details. So today we're going to introduce a new potential source of EMF. So consider the following device. Consider following device. So the picture here is we have a conductor on the right, conductor on the left. We have a conductor in the middle. The conductor in the middle is not like glued to the conductor on either side. There is a magnetic field going into the screen throughout this whole area, right? I'm only drawing it in those places. And the conductor is moving downwards with some speed v. Here's our magnetic field. So this just looks like some arbitrary thing, right? But we can actually, will this be on the, no, this material will not be covered on the midterm. This is chapter 5, it's not covered on the midterm. So we can ask what happens to the charges in the conductors, right? So charges in conductors are free to run around, they're free to move wherever they want. So if there's a force on those charges, they will move. They will experience the force, they will accelerate, and they will obtain a velocity. So as the rod moves downwards, we can ask what happens to the charges in the rod. The charges in the rod feel a magnetic force, right? And the reason they feel a magnetic force is because they're moving downwards and they have charge and they're in a magnetic field. So you can find the magnetic force on them using Q, or F equals QV cross B. So we can actually establish what direction it is. So if we have a positive charge and a negative charge in the middle, the positive charge is moving downwards and there's a magnetic field coming into the screen. So Q times V, V is downwards, cross B is in. So the force that it feels is to the right. So positive charges will feel a force to the right. Negative charges, well, it's the same thing, except the Q here is negative, so they would feel a force in the opposite direction. So negative charges will feel a force to the left. So here we have negative equals left, positive equals right. And so what we end up with, because these charges feel these forces, and every charge at every place will feel forces in the same direction. So if you have a positive charge on the right, it will experience a force that's still pointing to the right. What we end up with is we end up with the following scenario. Let me see if I can copy this. Copy. Nope, that was paste. Copy. There we go. So what we end up with is go away. We end up with a bunch of positive charges over on the right side. And remember, it's connected to this conductor. So you'll have positive charges on the right conductor as well. A few positive charges, a few negative charges, and then negative charges on the left side. So what we end up with, just by moving this conducting rod downwards, what we end up with is a separation of charges. And that separation of charges produces, this isn't a capacitor, by the way. This is, but the charges are separating, which causes a potential drop, right? When the charges separate, there will be a potential drop. And so we can figure that out. But this isn't a capacitor, just so you guys know. So the question is when does this go forever until there's no charges in the middle and all of the positive charges are on one side and all of the negative charges on the other? Obviously, the answer has to be no, because if there were no charges in the middle, well, like everything is made of protons and neutrons, or protons and electrons and neutrons. And so if all the positive charges were on one side, all of the negative charges were on the other side, then there would be only neutrons left over. And that's definitely not what happens. So at some point, these charges stop accumulating. So the question is, when do the charges stop accumulating on either side? And it's a question that we can answer by analyzing the forces. So there are two forces acting on any given positive charge. There's the magnetic force that pushes the charges to the right. This is for positive charges. And the, or I suppose that this is, well, yeah. For positive charges, the magnetic force pushes the charges to the right. The electric force will pull the charges to the left because the positive charges are attracted to the negative charges, which are on the left. So the net charge on any given, the net force on any given charge, and I'm doing this not as a vector, this is the net force in the x direction, is just the charge times the electric field that's established by separating these charges minus V times B. Now, the reason why it's V times B is because, remember, the Lorentz force is Q times E plus V cross B. Sorry, this should be, let me get this right. This should be V V times B minus E. There we go. It doesn't actually matter for the argument I'm about to make. But so the electric field points from the positive to the negative side. So that's why we have a minus sign here, because this is the force in the x direction. And the electric or the magnetic force, well, V points downwards. Magnetic field is into the board. So the magnetic force is to the right. So it's just the product of their magnitudes in the I hat direction. So it's to the right. But anyway, that is the net force on a given charge. And so the charge is at equilibrium, i.e. it experiences no net force when E is equal to VB. So when the electric force balances the magnetic force, you get no more charge flow. And that will be true all throughout the rod. And so there will be a point when the electric field gets large enough, because you've accumulated enough charge, that the electric force cancels out the magnetic force. So we can actually relate the electric force, the electric field here, to the potential, the potential difference between these two plates. That's not particularly challenging to do, because the electric field, this is, you have charges on one plate, charges on another plate, so there's a constant electric field between them. The potential difference between the plates is just E times the distance. Let's call this distance L. Right? Because it's just a delta V is equal to E dot dl. So we already know what E is. E has to be equal to VB when the charges have finished separating. So this is equal to V times B times L. So the point that what I'm getting at is that the motion of this bar in a magnetic field produces a motional EMF. That's what it's called. It's a technical name, motional EMF. Given by VBL. I can't write. And so the point is just by moving this bar downwards through the magnetic field, you're causing a voltage to build up between the two ends of the bar. And that voltage can function as a source of current. The reason why it can do that, by the way, is because if you complete this circuit, like, you have it go around this way, you'll have positive charges that will leap off, go through the current and join back with the negative charges. And that will reduce the electric field. And so you'll have another charge from the middle be pulled over to the right. And it'll just keep cycling through. The positive charges will make it back here. They'll be pushed over to the right, and then they'll cycle through the current, or cycle through the circuit. And there will always be this motional EMF that can provide whatever current is needed for the circuit. So the question then is if you can use this motional EMF just like a battery, so imagine that you just had two ends, like two terminals on this, and you put a black box here. You can just put this in the same place that a battery would go, and it would still function the same way. You would have a constant voltage across your terminals, and you would have a source of current or it could provide as much current as needed. That's exactly what a battery is. So a battery provides power to a circuit, right? It gives off energy. So the question is, in this case, where does the energy come from? In the case of a battery, it's chemical energy. In this case, it's not nearly as straightforward. It's not a question mark. Where does the energy come from? And just as a quick aside, in order to have a constant EMF across this device, constant voltage, you have to have that the velocity is constant, right? So we're going to assume that the bar is just traveling down at a fixed rate. And so it can't be the case that the energy is coming from the kinetic energy of the bar, right? It has a constant speed. So the kinetic energy is staying the same. So the question is where does that energy come from? So just as a quick reminder, remember that if left to their own devices, if you start a charge moving in a magnetic field, it will move in a circle, right? It'll want to go clockwise or counterclockwise in a constant magnetic field. However, in this case, the charges are constrained to only move left and right. So if we look at what what kind of motion a positive charge would want to undergo, well, let's figure that out. So let's say that the positive charge is moving, so it's moving downwards, comes in, it gets forced to the right. So it starts moving to the right a little bit. So its velocity is now downwards and to the right, and the magnetic field still inwards. So now it wants to feel a slight force up and to the right. And if it was allowed to keep going, it would eventually be moving wholly to the right, and then it would feel a force upwards. So these charges are really trying to escape the rod, and the negative charges do the same thing. But they can't, they're held in place by the rod. And so what actually happens is that there is some force that prevents the charges from moving upwards, from escaping the rod. That's basically a work energy type force that keeps the charges bound in the object. But the end result is that there is another force acting on the charges, keeping them in place. And so from Newton's second law, what we end up with is a force from the charges on the bar that pushes the bar upwards. So there is a force from the charges on the bar upwards. And so in fact, oh God. Okay, good, I'm recording. To keep the velocity constant, you're actually fighting against an opposing force. So we need an external force. And that force does work. So that external force, which pushes down on the bar to keep it moving at a fixed velocity, that does work. And the amount of work that it does is precisely the amount of energy provided by the device. And so it's actually kind of weird, right? Like you start, if you take two plates and then you drop a bar and there's a magnetic field and then you drop a bar, it'll actually eventually just slow, assuming there's no gravity. And if you want to keep it moving at a fixed rate, you have to keep pushing it down. Yeah, this is a very, very basic example of a generator, actually. But yeah, so there are a few examples about motional EMF that you guys should take a look at. One of them is in the Young and Friedman book, and it's about the motional EMF of an object that's in orbit. So imagine for a moment, well, you guys know that the Earth has a magnetic field. And so if the Earth has a magnetic field and you have some metal object that's moving in orbit around the Earth, well, there might be some motional EMF. There might be some potential difference that develops on the conducting object for that reason. And so you can go and calculate that. It's actually an interesting problem. There's another example in the Libre text, which is just about plates being separated by a wire, and the whole thing is moving. It's also a good example just to get your practice in. But we can start to generalize now. So this is a phenomenon where here you have this object moving through a constant magnetic field, and that seems to produce an EMF, and that EMF can drive a current if there was a resistor or if this circuit was completed and so on. So we can generalize this to produce EMFs via what's known as magnetic induction. So the idea here, we're going to be talking about Faraday's law. And we're going to generalize this idea of motional EMF to more useful ideas. So instead, let's consider the same system, but we're going to complete the circuit just to give it some context. So we have, so it's a really simple circuit. You just have some conductors. U-shaped conductor, say. And then you have your bar in the middle. It's the same thing. You have a magnetic field going into the screen. And so we've already established that you'll have positive charges on the right, negative charges on the left. And so you'll have a voltage, or you'll have a potential difference. You'll have higher voltage here, lower voltage here. And so you'll have current that flows this way. Let me use a different color for current. Because you'll want, these positive charges will want to rejoin with their negative charges. They can't go back the way they came because there's a force pushing them that way. But once they leave the bar, there's no more force pushing them, so they can go back and join their negative charges on the other side by going around the circuit. So let's call this height y. Let's call this length L. We're going to need these values in a moment. And let me fill this in just to make it so it's a little bit clearer. Those are conductors. Right, so remember before when we were first talking about, like when we were first talking about magnetic fields, there was the Gauss's law for magnetism. And so Gauss's law for magnetism was the following statement. It's that the flux through a closed surface of the magnetic field, i.e. B dot dA over a closed surface, that this vanishes. But it doesn't have to be the case that the flux through any surface is zero, right? This is only for a closed surface. So if you have like a sphere, the flux through that sphere is zero. But if you have a hemisphere with like an open bottom half, then you could have magnetic field lines coming in and passing through. And so the flux through that would not be zero. So that is to say, B dot dA for a non-closed surface is not necessarily equal to zero. It can be zero, like if there's no magnetic field, then it's zero, but it doesn't have to be zero because you can have magnetic fields that just pass right through. And so in this case, we can actually consider the flux through this surface. I'm just drawing that temporarily because otherwise it'll get too cluttered. But we're going to consider the surface that's enclosed by the circuit. The magnetic flux, which is phi sub b, at any given instant in time can be computed. And it's not particularly hard to do so, right? Because we can just do this integral explicitly. It's like you can just coordinatize it in the x and y plane. You can just go from like integrate from say 0 to y and 0 to L. And then you do b k hat, and then anyway, you guys know how to do this integral. It's a surface, it's a relatively straightforward area integral, basically. In this case, it simplifies to B dot dA, which is just because the magnetic field is constant and because the magnetic field points in the same direction as the area vector. By the way, we have to choose a direction for the area vector. We're going to choose clockwise in this case. We get that this is equal to B times L times Y. So this is the area, and this is the magnetic field. It's the magnitude of the magnetic field. Right, so the flux is just how much magnetic field there is times the area of that the magnetic field is passing through. In more complicated cases, the magnetic flux is more complicated, but here it's very, very simple. And so now, just as a quick reminder, earlier, the magnitude of the EMF and yeah, so in order for this to be precise, we actually have to decide what direction the area vector points in. And so really what I'm actually getting at is that the magnitude of the flux is equal to B times L times Y. So if the area vector either points into or out of the screen, right? Or into or out of the screen, because it's in the plane of the screen, and we have to pick one. And so let me get rid of the magnitude symbols there. We have to pick one of them. But regardless of which one you pick, either you'll get B is pointing in the same direction as the area vector, or B is pointing in the opposite direction. If it's pointing in the same direction, then the flux just is BLY. If the flux is in the opposite direction, then the flux is negative BLY. And so all I'm saying is I'm just talking about magnitudes here. So just as a quick reminder, earlier we talked about the EMF. This is actually a magnitude. I was being sloppy with signs here, but the point is the EMF could be positive here and negative here, or if the velocity was pointing in a different direction, or if the magnetic field was pointing in a different direction, you could have had negative here and positive here. So all I'm getting at is that this statement is really a statement about absolute values. So I'm actually going to fix that. There we go. The absolute value of the EMF is V times B times L. Right. Right. So the question is how do we relate these? So first, note that the velocity of the bar downwards is related to the height of the circuit, right? If the velocity is going downwards, so y is decreasing. And so the velocity is just the negative time derivative of the height. And you guys should go, if you don't follow that immediately, go back and think about it. It's good to have that geometric intuition. And so what we establish is that the EMF, the magnitude of the EMF is actually the magnitude of negative dy dt. And I can put magnitudes there, that this is already positive. I'm going to put magnitudes there. Minus dy dt times B times L. Now, the magnetic field is constant here. The length is constant, like the horizontal length. So this is just the magnitude of the time derivative of BL times Y. And so we get that this is equal to the magnitude of the time derivative of the flux through the circuit. So BLY is the flux, ddt is the time derivative, and this is a magnitude. So this is kind of remarkable that we can relate that the EMF in the EMF developed by this moving rod, the EMF developed in this circuit, is just related to how much of that magnetic field is enclosed by the circuit. And in fact, it's related to the rate at which the magnetic field enclosed by the circuit is changing, or the rate at which the flux is changing, rather, which is strange, but useful. And in fact, this is exactly what we observe. God, my neck is killing me. Probably should stop doing that. So generally, magnetically induced EMFs, and this is an example of a magnetically induced EMF. Motional EMF is a type of magnetically induced EMF. Generally follow this rule, that the EMF that is induced by the change in flux is related in this way. So what is the surface we calculate the flux through again? It's through any surface that has this circuit as its boundary. Any circuit. So like if we were viewing it from the side, it could have been this area, or it could have been this area. It doesn't actually matter which one it is. It's just any surface that has the circuit as its boundaries. So let me write that. So this is over a surface with boundary with the circuit as its boundary. Yeah, Stokes' theorem is really, really powerful. Like remarkably so. This isn't quite Stokes' theorem, but it's related. In fact, the divergence theorem is just Stokes' theorem. The fundamental theorem of calculus is just Stokes' theorem. Everything is Stokes' theorem. All of calculus, Stokes' theorem. We could talk about that later, though. So the question then is, so all magnetically induced EMFs obey this relationship. In fact, this defines what a magnetically induced EMF is. If you have a changing flux in a circuit, then there is a magnetically induced EMF that's given, or whose magnitude is given by this value here. So let's talk about magnetically induced EMFs. So let's consider that example that we just talked about, but I'm going to simplify it. I'm just going to draw less of it. But we're going to have a resistor here, a resistor. So here we have the picture again. So we have a resistor here. We have our bar that's moving downwards. We have the EMF, magnitude of the EMF is VBL. We have a positive side over here and a negative side over here. And so just so you guys can see this, you still have these magnetic fields that point into the page, or into the screen rather, right? And so we established that the current will go around this way. And the reason is because the positive charges try to get back to their negative counterparts because they're attracted to each other, but they can't go back the way they came, so they have to go all the way around through the resistor. We'll give that resistor a value of R. And now we can just go and do some calculations, right? So let's say for a moment that I just handed you this circuit. I didn't tell you that there's an EMF from the rod moving. I just, like a week and a half ago, I just said, okay, so you have a rod moving downwards. There's a resistor here. What's the current through that resistor? You may have said it's 0. And the reason you may have said it's 0 is because using the loop rule, you would get that you just have minus IR, we're going around clockwise, by the way, equals 0, which would imply that the current is 0. But this is wrong, right? Like we can do this experiment and we observe a current. So that means that there must be a mistake that we made. So in fact, we actually have to adjust our loop rule, and we'll see another way that we don't have to adjust our loop rule and it can instead add something else. But for a moment, we have to adjust our loop rule because we have to somehow account for the fact that there is this motional EMF that's not caused by a battery, it's not caused by a capacitor or whatever. So here we have that loops no longer add to 0. But instead, the rate of change of the flux. i.e. a sum over the loop of the change in voltage as you go around that loop. So you cross the resistor, you get some change in voltage, you cross the capacitor, you get a different change in voltage. This should be equal to d phi dt. i.e., let me write this a little bit better. And that's an integral of a closed loop of b dot. I need a time derivative here, ddt of b dot da. So it seems like we have to just throw out our old loop rule and use this one. And so in the cases that we've seen before, the magnetic flux through the circuits, like up until now, was always the same. It was, well, it actually wasn't, but we approximated it to be constant. And so it did just add up to 0, because if the magnetic flux is 0, then there's nothing on the right-hand side. But if the change in magnetic flux isn't 0, then you're a bit out of luck. So just as a quick note, the question then is why is it a plus sign there instead of a minus sign? So we've established that, or the reason why we want to add a term over here like this is so that we get that, for example, in this example, we would get that, minus IR. Let me rewrite this. We would get that E is equal to IR. We want to be able to get that result. So we have to put the induced EMF on the other side. And so the question is, did we get the sign right here? Should that be a minus sign? And so I propose to you that this is correct. As written, this is correct. But I need to justify it. So let's talk about that wrinkle. So the result that we got before was a result about magnitudes, right? So we can't just say that the EMF is equal, the induced EMF is equal to the rate of change, time rate of change of the flux. It could be equal to the negative, and we wouldn't know from what we've already established. So we need to figure out why this is plus instead of minus, for example. I need to justify this to you, otherwise I will feel bad. So let's just work out the case above. So in the example, the one with the moving bar and all that, we should have, like the formula that we should end up with is IR equals VBL. That is the formula that we should get, right? And this side is positive, this side is positive. It should just be hunky-dory like that. So in this case, VBL is positive, but the time derivative of the flux is negative, right? So if we go look at this circuit, the flux is decreasing because the area is getting smaller and the magnetic field staying the same. So here we have the time rate of change of the flux is negative. So we need, for our formula, we need that IR is equal to the negative d phi b dt, the negative time derivative of the flux. And so our loop rule should read, the newfangled loop rule where we, or the loop rule that we should get from this relationship, it should read minus IR is equal to d phi b dt. I just moved the minus sign over. And this does check out, right? That's the sign that we get over there. So that's good. Okay. So we chose the right sign. If I had a negative sign here, I would have been wrong. And I would have been wrong because it doesn't agree with what our loop rule should read, which we establish here. So the question then is how do you determine the sign of an arbitrary change in flux, right? Like that seems like it could be hard. And by the way, I know that I'm throwing a lot of like there's signs and loop directions and clockwise, counterclockwise. I understand that this is challenging. There is a simple way to encapsulate all of these ideas, which we will hopefully get to today. So let's first do the hard way and then we'll get to the easy way. So how do we determine the sign of an arbitrary flux or rate of change of flux? So in principle, you would just be able to say, oh, well, the rate of change of the flux is just if it's positive, it's increasing, and it's negative if it's decreasing. But that's not quite there, right? Because it could be the case that the flux is negative, but it's getting less negative. That would have a positive rate of change. Or it could be the case that it's positive and getting more positive. That would also have a positive rate of change. But they would have different rates of change of the magnitudes. So we need to actually figure out how to establish what the direction of the flux is. And in fact, I made that built-in assumption here because I said that I made an assumption here. And in fact, that assumption depended on the direction of current that I guessed the loop would go in. So when I did this loop rule, right, I assumed that the current was going clockwise and that we were going clockwise as well. And so that gave us a negative sign in front of the IR. There was built-in information there that I kind of shoved under the rug. But the formal way to handle this is there is a well-defined choice of the area vector, which will determine the sign of the flux and hence whether it's increasing or decreasing. Right, so when you guess the current direction, and by current direction, I mean the direction of current flow in the loop. It could also just be an arbitrary assignment of a direction. It doesn't actually have to be associated with the current in any way. It's just, you just have to choose what direction means going around the loop in a positive manner, clockwise or counterclockwise. So when you guess the current direction, that determines, that direction that you chose determines the direction of the vector, the area vector, A, by the right-hand rule. So if I determined that the positive direction, the positive circulation of this loop is clockwise, then the area vector that's associated with that positive direction of the loop points into the screen. And so that's how I could establish that the flux is positive, because the area vector points in the same direction as the magnetic field. So that there is a formal way to determine the area vector of a loop. You have to choose which direction is positive when you go around the loop. That will tell you what direction is out of the loop using the right-hand rule. So in the case above, we found that the area vector and the magnetic field point into the screen. And so what we can establish from there is that the magnetic field dotted into the small area component is greater than 0. And that's just because A and dA point in the same direction for simple surfaces like this. And so we have phi sub b, which is equal to the integral of b dot dA. So you're integrating a bunch of positive things. So you're adding up a bunch of positive numbers. You get a positive number at the end of the day. And then we know that the magnitude of the flux is decreasing, right? The area is decreasing, magnetic field staying the same. So the magnitude of the flux is decreasing. And we know that the flux itself is positive. We have that d phi dt, the rate of change of the flux, is negative. So the reason why we needed to establish whether the flux was positive or negative was because, for example, we knew the magnitude was decreasing, but if the flux was negative, that would mean that it's going from a large negative number to a smaller negative number. And that would mean that the rate of change of the flux is actually positive, because it would be like going from here to here, which has a positive slope, right? So in this case, we're going from a positive flux to smaller positive flux, so negative slope, hence negative time derivative. So that's how you figure out whether the flux is positive or negative. It's a bit involved, and you have to make sure that you're being very careful, otherwise you will make a sign error. And again, we will talk about the easier way to handle this in a minute. But before we do that, there is a different way to handle induced EMF rather than talking about flux. We can fix our loop rule so that it still adds up to 0 by just subtracting this to the other side, right? That's what we're going to do. And that's what we'll typically do. So this is arguably a better way to handle induced EMF. Another way to handle induced EMF is to introduce a new term in your loop which accounts for the change in flux. And so instead of having our loop rule not add up to 0 and you have this change of flux on one hand, really, we just fix our loop rules so that it looks like this. So we have an integral of we're adding up all the contributions around the loop, and then we add in we add an extra term, which is the induced EMF, and that has to add up to 0. And so then we can establish the induced EMF is what it needs to be so that the sum of so that this formula above is still true. It's fixed to make this statement sum over delta V is equal to the rate of change of the magnetic flux. So that is the induced EMF is equal to the negative rate of change of the magnetic flux. So all of this work was to get at this formula, and we're going to generalize it in just 1 second, because what we had established before, let me find it, is that we only knew a relationship about their magnitudes. We only knew a relationship about their magnitudes, so we needed to know whether they're related by a positive or a negative sign. The magnitude of the flux is decreasing because the area is decreasing as the bar goes down. The area enclosed by the circuit is decreasing, and the magnetic field is staying the same. I'm actually not going to put a box around this. But this is where we were headed. We wanted to be able to establish that it's a minus sign that belongs there to get that relationship. And so in the case where the circuit is made up of a bunch of coils, of say n coils, or of a coil of n turns, so think like a solenoid, then the flux through each of those loops, each of those turns, contributes to the induced EMF. And so we end up with actually the induced EMF when you have n turns is negative n times d phi b dt. And this equation I will put a box around because this is known as Faraday's law. And in a sense, this is an integral form because the EMF is a line integral around the loop and the flux is a surface integral. And we will get to a local-ish form of this later. And that I believe that'll either be on Thursday or on Monday, or sorry, I think that we have the midterm on next week, but it'll either be on Thursday or the time afterwards, because we'll see that changing magnetic fields induce an electric field. All right, so now we have a lot of discussion to go over in 7 minutes, which we can at least get to part of it. So, like I said, there was a lot of discussion of signs floating every which way, and you induce currents in a certain direction, and the flux is changing in a certain way, and so on and so forth, which can be really confusing. And so, fortunately, there is a very useful kind of rule of thumb that you can use to establish what direction does the EMF point in, i.e., what direction will it try to establish current flow, right? And the basic gist is that, look, the EMF that's established in this circuit, even if we didn't know what was happening, we could have established that it will create current flow that is going clockwise here just by noting how the direction of the magnetic field and the way the flux is changing. So I want you guys to consider the following thought experiment, and this is laid out in more detail in the lecture notes, but I'm kind of just going to talk you through it. So let's say that you have a loop. I'll just sketch it out. So let's say that we have a loop with no current flowing through it, suddenly placed in a place, or suddenly moved to somewhere where there is a magnetic field, and that magnetic field is large. So loop is suddenly experiencing a large perpendicular magnetic field. So what was experiencing no perpendicular magnetic field, now it's experiencing a lot. So we know that the magnetic field went from 0 to not 0 very quickly. And in particular, then the flux through that loop goes from 0 to not 0. So we know that there will be some induced current flow, right? Anytime you have a changing flux, you'll have some EMF, and that EMF will produce current. So the question is, what direction does the current flow in? So the picture is something like this. You have your loop, you have your magnetic field, say into the screen, suddenly gets very, very large. So we could go slog through all the signs and all the conventions and things that we established earlier, but we can do it easier. We can kind of just guess and check and see what happens. So let's guess that the current flows, let me write this out. This is the current induced by the EMF. So let's guess. Let's say clockwise. Right. So if it was clockwise, then the current flow that is, then the EMF that causes current to flow clockwise, that current will create its own magnetic field, right? When you have current flowing in a loop, there will be a magnetic field in the middle, and we can use the right-hand rule to establish what direction that magnetic field is in. In that case, it would produce more magnetic field in the direction of the external magnetic field. It would increase. This increases the flux through the loop, because the induced current would create a magnetic field pointing in the same direction as the externally applied field. And so the flux through the loop would increase. And then because the flux increases, the current would increase even more, which would create more flux and back and forth forever. And you'd get a runaway effect. You'd end up with infinite amounts of current and infinite magnetic field. So we know that that can't happen, because that would require infinite energy, and we know that we don't just generate black holes out the wazoo when we put loops in magnetic fields. So the current cannot be flowing in that direction. Otherwise, it would require infinite energy. Instead, if we guess counterclockwise, we would find that the current produced by the induced, or the current that is flowing because of the induced EMF, if you had the current going counterclockwise, use your right-hand rule, that would produce a magnetic field that's in the opposite direction of the applied magnetic field. So current flowing counterclockwise would decrease the flux through the loop, which would reduce the induced current, which would reduce the correction to the magnetic field, and it produces, at the end of the day, it produces a negative feedback loop. And so what you'll end up with when you do this, if the current does flow counterclockwise, which it has to because it can't flow clockwise, is you'll get a sudden spike in current flowing counterclockwise, and then it'll fall off because the change in the flux from that sudden spike will be smaller than what it would have been without that sudden spike. And so you'll get a ever decreasing flux, or an ever decreasing rate of change of the flux through the loop, and so the current will decrease and so on until there's no current flowing through the loop. And we know at the end of the day there should be no current if you wait long enough, because at the end of the day the flux through the loop is just the externally applied magnetic field times the area of the loop, right? So it should just be constant if you wait long enough. There might be some transient effects, but it should just be constant. And so from just the simple thought experiment, we can actually kind of generalize the idea to something called Lenz's law, which is a good way to figure out what direction the induced current would flow. By the way, I'm often going to use the phrase induced current to refer to the current that would be produced by the induced EMF in a magnetic field. It's just that it's sloppy on my end, but it just makes it easier. Otherwise, I start talking about the current produced by the induced EMF and it gets messy. Right, so Lenz's law is the following statement. So I'm going to write this out precisely and then we'll be done. The EMF induced in a circuit is such that it produces a current that creates a secondary magnetic field. Secondary magnetic field that seeks, and obviously it doesn't seek, we're anthropomorphizing it here, but it seeks to undo the change in flux that the induced EMF, seeks to undo the change in flux that induced the EMF in the first place. Put a box around this because this is actually super useful. So just as a quick note, and then we'll call it a day. And we'll talk about this more on Thursday. But so the induced EMFs don't actually have to produce the only current in a circuit, right? Like you could have a battery, like a real chemical battery in a circuit that has current flowing through it, and then you could suddenly change the EMF. Sorry, you could suddenly change the flux through the circuit, and that would result in a induced EMF, which might be in the opposite direction of the battery. And so what might happen is you would have the induced EMF kind of would want to produce a counter current to the direction of the current actually, and so all it would do is it would decrease the current that's flowing through the circuit. And so I'll give a more concrete example of that next time. But I'm going to end here. And